So we're going to be finding the trig ratios of reference triangles. And what a reference triangle is it refers to the triangle made between the terminal angle or the terminal side of an angle and its reference angle. So for this angle right here, this is going to be the terminal side, and the reference angle is going to come down to this x-axis right here. So when we're finding trig ratios, let's start by identifying what our trig ratios are. So first we have sine of theta, and our theta is our angle to be generic, cosine of theta, and tangent of theta. And usually when we have sine, cosine, and tangent, sine is going to be the opposite over the hypotenuse. I'm going to abbreviate. Cosine is going to be the adjacent over the hypotenuse, and tangent is going to be opposite over adjacent. And this is your SOHCAHTOA. And these are your generic forms of your three trig ratios. So with our triangle that we have right here, if this right here is our theta, our opposite is going to be this leg right here, which is the same as our y coordinate, because if this is our y, we're going to go up the same number as y. So this part right here is going to be y. And this part right here, this adjacent side, is going to be the same as our x coordinate. So for example, if it was 3, 4, this distance right here would be 3, and this distance right here would be 4. So this is x and this is y. So when we're talking about our trig ratio right here, our opposite is our y, and our hypotenuse is this distance right here. And we call this distance r. And we call it r because it's the same as a radius of the distance of this of the origin to this point right here. So it's the radius of the distance from here to here, and it's always a distance. And because it's a distance, it's always going to be positive. And we can find this through a couple of ways, as we'll see later. But for now, we're going to stick with r. So our hypotenuse is r. For cosine, cosine is adjacent over hypotenuse, and our adjacent is x, and our hypotenuse is r. And then tan theta is opposite over adjacent, y over x. This is going to be the trig ratios, the three trig ratios that you guys know for any coordinate point. These are three, and there are three more that you guys haven't learned yet, and we call those the reciprocals. And we call them the reciprocals because they are equal to the reciprocal of the ones that you guys know. That's why there's three more. So for example, one of our reciprocals is 1 over sine theta. We call this one cosecant. And the easy way to remember that is because we're flipping it, the s and the c flip. So if I know that I want the reciprocal of sine, the first letter is going to be c, so I can figure out that this is cosecant. So this is the same as 1 over what we have right here, or the reciprocal of this, which is hypotenuse over opposite, because if we have the reciprocal of sine, we're going to have the reciprocal of this part. Our next one is going to be 1 over cosine. This one is called secant, and again the c and the s flip. And the reciprocal of cosine right here is hypotenuse over adjacent. And finally, we have the reciprocal of tangent, 1 over tan theta, and we call this one cotangent, denoted as cot theta. And the reciprocal of this is going to be adjacent over hypotenuse. And now we need to figure out what that means for our reference triangle and the point that we have. So the reciprocal of y over r is going to be r over y. The reciprocal of x over r is going to be r over x. And the reciprocal of y over x is going to be x over y. And these are our 6 trig identities that we now know. So here I have a coordinate plane where I've labeled each of our axes. This one right here is the positive x. this one over here is negative x, this is positive y, and this is negative y. And we know that this is quadrant 1, quadrant 2, quadrant 3, and quadrant 4 in this order. So when we're talking about our trig identities, and I'm going to stick to these three to keep it simple, whenever we have positive x and positive y, all of these values are always going to be positive because y over r is always positive, and in this quadrant, y is positive. And this same thing for cosine, r is always positive, and for this quadrant, x is positive. And over here, we have y and x are positive. So in this one, in this first quadrant, all of our trig values are going to be positive. For cosine over here, for the second quadrant over here, we have a negative x and a positive y. So if we have a negative x, our cosine is going to be negative and our tangent is going to be negative because we have a negative x over a positive number and then y over a negative number. Negative x over a positive number and y over a negative number. So these two are going to be negative, but this one, however, it will be positive because this one is not affected by our negative x. So over here we have sine is positive, and this would also be cosecant as well because it's just 1 over sine, but we're just going to stick with s for right now. For this third quadrant, we have a negative x and a negative y. So over here we'd have a negative over a positive, this would be negative. Same thing here, we'd have a negative over a positive, so this would be negative. But over here we have a negative over a negative, and that would give us a positive number. So that's why we say right here, tangent is positive because we have a negative over a negative. And it would also be cotangent, but like I said, I'm going to leave that out for right now. And over here, we have a positive x and a negative y. So this negative y would make our sine negative, and it would also make our tangent negative. But because we have a positive x right here, our cosine is still going to be positive. So over here, we have that cosine's positive. And same thing over here, we also know that secant is positive because it's just 1 over cosine. It's not going to change the sign. And an easy way to remember this, which is not very school appropriate, is still all strippers take cash in the order of the quadrants. So A, S, T, C. And this is how you know which functions are positive. And you can also just figure it out by going through the positive x, positive y, negative y axes. So now let's work out a couple of examples. Here I have the point negative square root of 2, 1, and that's this point right here. And this is when we're trying to figure out what our triangle is, we're going to draw a line from the origin to this point right here. And how I like to set up these problems is I know that I'm always going to need x, y, and r to figure out all of our trig identities, which is what we're trying to do here. So I start by saying x equals, y equals, and r equals, and filling them in as I figure them out. So here we have x and y because we're given a coordinate point. Our x is going to be the x value of this coordinate point, which will be negative root 2. Our y value is going to be the y value. Our y is going to be the y value of this coordinate point, which is going to be 1. And r is the distance from right here to right here, and it's the same thing as this hypotenuse. So you can do one of two ways. You can either use the distance formula from the origin to here, or you can treat this as a right triangle, which it is, and use the Pythagorean theorem. Both give you the same answer because the distance formula is derived from the Pythagorean theorem. And you can prove that yourself because we'll see it here. And I'll go ahead and walk through the distance formula just to show you guys that they're actually equal. So the distance formula is the square root of x1 minus x2 squared plus y2 minus y1 squared. Or x1 minus x2, sorry. So if our x1 and y1 are this point right here, x1 comma y1 equals negative square root of 2 comma 1, just making sure I'm still in range, x comma 2 comma y comma y2 equals 0, 0, because that's our point right here. We see that the square root x1 is negative square root of 2 minus 0 squared plus y2, or y1, 1 minus 0 squared. We get negative root 2 squared plus 1 squared. So at this point, I've plugged into the distance formula, and when we're going from the origin, it's actually minus 0 for both of them. So it turns out that we get the square root of the sum of the squares, which is the same thing as the Pythagorean theorem. Just an interesting side note. So when we're finding this, negative square root of 2 squared is just 2, and then 1 squared is 1, so we get r equals the square root of 3, which is what we just went through and found. Alright, now we have x, y, and r, and we're ready to find all of our trig functions. So our first trig function will be sine theta equals, I'm going to write all of them out, tan theta. So sine theta we found is y over r, so that's going to be 1 over the square root of 3, and we wanted to rationalize this, it's the square root of 3 over 3. Cosine theta is going to be x over r, negative square root of 2 over the square root of 3, which is the same thing as negative square root of 6 over 3. And this is rationalizing it. And tan theta is going to be y over x. So 1 over the negative square root of 2, which is negative square root of 2 over 2. So all I've done here is I've plugged in to my formula for sine, cosine, and tangent. And now I need to find the 3 other trig identities. And I'm going to write them below them because I don't have space over here. But usually what I do is I write them next to the one that they are the reciprocal of. So for example, for sine, the reciprocal of sine is cosecant, so I'd write cosecant right here, but I just don't have space. So I'm going to write it down here. Cosecant of theta equals, it's the reciprocal of this. And I actually use this one before I rationalize because although you could write 3 over root 3, which is the reciprocal of this part right here, you'd have to rationalize again. So I just used this one before I rationalized. And the reciprocal of this one right here is just the square root of 3. For cosine, the reciprocal of cosine is secant, because the s and the c flip. And this one, there's no getting around it. The reciprocal of this one is the square root of 3 over the negative square root of 2. And when we rationalize, we get the square root of 6 over 2, negative 2, sorry. And then for cotangent, again, I'm going to use this one because it's before we rationalized, and we get the negative square root of 2, the reciprocal of that. And that's how we find the trig values, all 6 trig values for this point right here. So here we have a second example where they tell us that the tangent of big G equals negative 5 over 6. And big G is just like any other variable. We could have put theta here, we could have put x here. It doesn't really matter what we use here. Usually for angles we use capital letters just to differentiate from angles and from side lengths. So that's why we have a big G here, but this could be theta, it could be whatever we wanted it to be. So here we have negative 5 over 6. So whenever we have tangent of G, it's usually y over x. So that's what we have right here. We have y and we have x. That's what they gave us. So again, I'm going to make my columns right here. I have x, y, and r. And I know that y is negative 5 and x is 6. All right, so using this, I need to find the radius. And if I wanted to draw this out, I'll move this down for you guys. We would be 6 over here and negative 5 down here. We'd be somewhere over here. It doesn't really need to be specific, but the point is that this part right here is G. This is our right angle, and we know that this is 6 and this is negative 5. So we need to use the Pythagorean theorem to find R right here. Excuse me. So we're going to use the square root of the sum of the squares, so 6 squared plus negative 5 squared equals 36 plus 25, and we get the radius is the square root of 61, and that can't be simplified. So here we have the radius is the square root of 61. So now we have all that we need to find all the different trig values. So I'll just go through them. Sine theta, or sine of big G is going to equal y over r, so negative 5 over the square root of 61. But we've rationalized that, negative 5 root 61 over 61. Cosine of G is going to be x over this, so it'd be adjacent over hypotenuse, which would be this part, 6 over the square root of 61, which is going to give us 6 root 61 over 61, and that can be simplified. And then now we need to go through our reciprocal functions. So we started off with tangent. Let's go with cotangent. Cotangent of g is going to be the reciprocal of this, so it'd just be 6 over -5. Reciprocal of sine is cosecant, again because we had an s, and when we find the reciprocal of that we get a c. And the reciprocal of this is the square root of 61 over -5. And then our last one, cosine, the reciprocal of that is secant, and we get the square root of 61 over 6. And that is how we find the trig values for all of these. Now, a special case would be, and I'm going to mark off this part of the paper here for a second problem. A special case is when our point falls on an axis. So I'll call this point 0, 5. When this happens, let's set up our chart again, because this is how we're always going to do these problems. We need x, we need y, and we need r. X is going to be the same thing as always. It's going to be the x coordinate is 0, because this is 0 distance left or right. For y, it's the same thing, going to be 5. And the radius is going to be the part that trips a lot of people up here. You can still use the Pythagorean theorem. You'd still get the square root of 0 squared plus 5 squared. So you get the square root of 25, which is just 5. So we find that our radius is 5. An easier way of going about that is knowing that the radius is always the distance from the origin to our point. And we can see just by knowing this point is 0, 5, that the distance from here to here is just going to be 5. And we kind of need to ignore the fact that this isn't a triangle for a moment to find these sine and cosine values. The reason we can do that is because sine is defined, sine and cosine and tangent are all defined for all points on a coordinate plane, for reasons that I can't really get into. But we can still use our trig functions for points that are on the x and y axis. It's not that things get a little bit weird, but we can still do it. So here we have sine of theta equals cosine of theta equals tan of theta equals. So sine is y over r, opposite over hypotenuse. So 5 over 5 would give us 1. Cosine is x over hypotenuse, which is 0 over 5, which would just be 0. And tangent is y over x, 5 over 0. We cannot divide by 0, so what we find that when we try and find the tan of this number, this is undefined. And this is what I was talking about earlier when I said things would get weird. Our tangent right here is not defined when we're on this y-axis. Alright, so now let's find our reciprocals. The reciprocal of sine, cosecant, and that's going to be the reciprocal of this, so it's still going to be 5 over 5. It's going to be 1. Reciprocal of cosine is going to be secant, and that would be 5 divided by 0. Another weird thing, 5 over 0, we can't do that. So we find that the secant of this point on the y-axis is undefined. And over here we have cotangent of theta. Cotangent is going to be x over y, with 0 over 5 is 0. So when we have a point on the x or the y-axis, we find that some of our values are going to be undefined. And this is going to be consistent for things on the same axes. So like 0.04 right here, we would find the same things. We would find 4 over 4, 0 over 4, and 4 over 0. And if it was on the x-axis, the reverse would happen. We would find other values, but we'd still get so that some things are undefined. So you can still find the trig ratios. You're just going to see that some of them are actually going to end up being undefined. So that's what you need to look out for.